Try that again. Okay. So from what you said, all I had to do is just throw a region up there. And then the question would be, what does this have to do with what we're doing in class? But there's a lot more going on here. So yes, we're talking about regions in R2 and integrating a surface or a multivariable function over those regions. But there's something really, and there's a reason this is an animation, right? So what's going on here? Travis, what do you think?
Well, it has to do with those double integrals.
Yeah.
That we were working on.
Uh-huh.
And this one we're integrating from bottom to top and then from left to right.
Okay, so what you're saying, bottom to top comes first?
Yeah, so dy dx.
dy dx, and what kind of integral is that? Remember?
2.
Is that type 2? Yeah, so whether it's type 1 or type 2, that's just kind of what we're calling it, but you got it. So bottom to top first, then, so for a arbitrary x value, any x value, we integrate with respect to y, which means bottom to top, and then once we've done that, we get like a strip. And now we're going to integrate all those strips, starting from left all the way to right. So this animation is showing our type 1 order of integration. This is what we're thinking about when we do dy dx in that order. Bottom to top first for an arbitrary x, and then integrating all those strips starting from the leftmost x to the rightmost x. Does it make sense? Okay, so now what does this have to do with related to volume? What does it have to do related to volume? Yeah, Alex.
If you have some multivariable function,
Uh-huh.
fxy, then your double type 1 integral
Mm-hmm.
is adding your integral of dy and dx, which gets you the total like signed volume above that region between y and x integrals.
See if I can draw this. Kind of like that. How'd I do? I'm trying to recreate that in R3. Do you see that that's the same thing? Same thing in the xy plane, but in R3. And so if you have some, he said, if you have some multivariable function, say f, we're talking about double integrals, then the double integral of f dy dx, right? Which is, so again, regions are often called D, or we'll often call those D, so over D. Finds what? Sine volume. And what is sine volume? Somebody else? What is sine volume? Yeah, Brian.
It's the positive, it's the sum of the positive and the negative volumes.
Okay, so when you say negative volume, what do you mean by negative volume?
It means that we're allowing volume to go beneath the xy plane.
Okay.
At negative values.
Right. So when that multivariable surface curves underneath the xy plane, those values are negative. The values of the function are negative. So those volumes beneath the xy plane get subtracted as a contribution to this value. So another thing we call that is net volume. And what are those? So that is what? Difference of volumes. So both of those mean difference of volumes. All the volume above the xy plane minus all the volume carved out below the xy plane. So it's a difference of volumes. Do you see that? So that's what sine volume or net volume means. Okay, and so what volume, right? So what defines these solids? So exactly how is the solid defined? What's that? The region and the z values. Okay, so like what? So up and down. What is defining the top and bottom of these solids? What's defining the top and or bottom of these solids? Function. What else? Anything else defining the top and or bottom? XY plane, right? Function and XY plane define the top and bottom of the solid, right? And then what defines the sides? The region, right? The region extended like a cylinder up and down, right? So you take that region, that's like our red and blue and black region, you extend it up and down like a cylinder, and that gives you what the sides, defines the sides. So the solid defined by, this is top. So sometimes the top is the xy plane, right? When the function is negative, then the top is the xy plane, and the bottom is the function, okay? And then the sides are the cylinder from the region D, formed by region D. Okay, so that's an overview. And it's the third class in a row that we've talked about the meaning of a double integral. What's the meaning of a double integral, or geometry? In geometry, it gives us volume. Double integrals give volume, right? Sine volume, or net volume, which is difference of volumes. Okay, when does it give volume? When does the double integral truly give a volume? Yeah.
Or if f is a rate of change function.
No, because if the rate is negative, more negative than positive over d, then you're still going to. So the question I'm asking is in terms of geometry. So you're talking about accumulation and rate of change, but in geometric sense, when does that truly give a volume? What's that? Everything is positive. So what is it specifically that makes this a volume? Yeah.
If the surface for whatever region is either all above or all below the x.
Okay, so volume if f of xy is greater than 0 for all of d. So what about, you said all below too. So does it give volume if it's all below? If f is all below the xy plane, does it give volume? Is the opposite of the volume, right? It will be a negative value. So the magnitude of your integral will be volume, but you'll get the opposite of it, right? You'll get a negative value. Okay, so all review, but really important that you have these images in mind. Questions? Okay, so we're going to work more on double integrals today. So let me just, we'll do an overview here. So here's our type 1, bottom to function to top, then left to right. So that's dy dx, right? And we just saw it, right? So dy first, then dx. Okay? And then type 2 is left to right first, right? So you go left function to right function. and these functions are x as a function of y, and then bottom to top. So that would be dx dy, left to right, bottom to top. So we start left to right like this, and then those strips we integrate for dy, starting from the bottom up to the top. Okay, so here are some examples, and we want to practice with these regions. So it's the other way now. I'm giving you the integral, and we want to sketch the region, and then we want to change the order of integration to the other type. All right? So here's the strategy with these. Like it says here, sketch, first thing you do is sketch the region given with the given limits of integration. Okay? These double integrals are geometry problems. They're geometry problems. So we're going to start by sketching the region with the given limits. Then we're going to scrap the old limits. Get rid of them. Don't pay attention to them. The point is, you don't write the new limits from the old limits. You write the new limits from what? From your sketch. Okay, so we're going to use the sketch to write the double integral in the other order. These are geometry problems. They're geometry problems. So you need that sketch, all the details, and then like we've already done, once you have the good sketch, like we've done already, take that sketch and then write your new limits of integration for the other order. So we'll do the first one together, and then we'll spend most of the class working on these others. Okay? So questions on the strategy? Okay, so let's do the first one together. So what is our type here for this first one? dy dx means type 1, bottom to top, and then left to right. So this 3x, this is bottom is y equals 3x, and the top is y equals 24. So we got to sketch those, right? So y equals 3x and y equals 24. Y equals 3x is just a line through the origin. And then y equals 24 is like this. And so look, y equals 3x, what is that for the region? Which boundary is that for the region? Bottom. Y equals 24 is? Top, okay? So, are we talking about down here? Or are we talking about over here? Exhibit A or Exhibit B? B, because we want y equals 3x to be the bottom and y equals 24 to be the top. Now the question is, where does it start? Where does the region start? Where's the left side and where's the right side? So the left side is x equals 0. So here's the left side. And where's the right side? X equals 8. So 8 could be anywhere. It doesn't have to be this intersection. 8 could be here. It could be here. It could be here. But in this case, it does, because this is y equals 3x. Y equals 8 does happen to be the intersection, but it doesn't have to be. Do you see that? It would be totally valid for it to say this to be x equals 6. And then our region would be just that much. But x equals 8 does happen to be the x coordinate of that intersection. So that's where we're at. Okay, so now we've got our We've got a region. And what are we going to do? So we know we've got all the boundaries, x equals 0, y equals 24, y equals 3x. And our goal is to write it as type 2, which means it's the same function. The function doesn't change. Right? The function, so all the limits of integration are an R2 phenomenon, right? They're the region and the xy plane. And then this function has to do with what in R3, right? It's a surface, whatever the surface is in R3. So we want now type 2, which is dx dy. So what's the cheer for dx dy? Left to right, bottom to top, right? So left to right. So what are we going to do? So now we're going to go, for a typical y value, we're going to go left to right. We're going to integrate like this, across. So the left side is x equals what? 0. And then what's the right side? X equals. So it's the right side's an x value, but now expressed in terms of y, right? So x is y over 3. And then so left to right, bottom to top. So bottom means the first strip that we have is at the bottom. Is at what y value? Y equals 0. And then we're going to integrate all those strips up to the very last strip is at 24. So it's the integral. So changing the order here, the integral is from 0 to y over 3 and 0 to 24 dx dy. So you don't need to write the x equals and the y equals. I'm just doing that to clarify. It would just be, you just write 0 to y over 3 here, and then 0 to 24. And so the value of this is the signed volume of the function f over the triangular region D. And this, the value of this double integral will be exactly the same as the volume of this one. It's just setting it up in the other order. Any questions? Okay, so when you get to number 3, this is the sum of two integrals, but it represents one region D. One region D. Okay? So we've seen situations where we had a region and we had to split it up into two, right? We had to split it up into two subregions in order to write the limits. So this is the example, right? So this is an example of this, where you have the sum of two double integrals, and that those together represent one region. So you start out by sketching that one region, and then writing it in the other order. Okay, so we're gonna have about 15 minutes or so to work on these. You're either making progress or you're getting help. Yes, Tim?
Can you blow it up a little bit?
Oh yeah, sure. Be happy to. It's because of the necessity based on the boundaries. The boundaries are what necessitate whether you have to split it up or not.
What's the intersection?
So focus on the boundaries. So we're going to go, this is going to be type 2, right? This is going to be left to right. So does either the left boundary or the right boundary require that you split it up?
Oh, yeah.
So left to right means we're coming in this way. Do we always have the same boundary, or does it change? It changes. How many times? How many? Yeah. So you have this part of the left boundary and this part of the left boundary. And what about the right boundary? Stays the same. So that tells you how many integrals you need. How many integrals do you need? The right isn't a problem, right? The right is always the same, but the left, sometimes you're entering at x equals 2, sometimes you're entering at x equals y minus 1. That's why you need 2. It's not about how do you chunk this up. It's the fact that the boundary is split up. Is that better?
Yeah. So you split up.
You're gonna have, based on y from 0 to 3, and then 3 to 5, your x, your left side for x is gonna be different. Better? Does that make sense? Can I talk about number 3? Let's talk about number 3. So for number 3, I think this is really good because I think it's not about looking into the region and saying, how am I going to split up the region? That's not what determines how many double integrals you need. It's about the boundary. The boundary of this thing is what's going to tell you that you need more than one double integral or not. So we're given type 1, so now we're going to write this in type 2, right? So type 2 means what to what first? Left to right. So we're looking at the left boundary and the right boundary. That's what's going to determine if we need to split it up or not, the boundaries. Not what's happening inside the region. So left boundary, is it always the same or is it split up? Do you see that it's split up? So it's this vertical line up till y equals 3, and then it's the y equals x plus 1 from 3 to 5. See that? Was that no? The left side of this, entering into this region from the left. Sometimes for low values of y, 0 to 3, you enter in through x equals 2. For higher values of y, from 3 to 5, you enter in from the left side at y equals x plus 1. Is it better? The left side of this, right? The left side is this right there. Here's the left side. This is the left side of this region. Do you see that? If I was firing an arrow from the left into this thing, where would the arrow pierce into the region? That's the left boundary, which is split up between that and that. That's the left. What about the right side? Red for right. What's the right side? It's where the arrow would leave the region. If I fired arrows through this thing, where would it leave? Just the one, right? It's always the same. So the blue is the left side of this, and the red is the right side. Do you see it? So that determines whether we're going to need to split it up or not. Do we need to split it up into more than one? How many? 2. We need one for this and this. So it's the limits are not about, oh, I want to carve this region up into these sections. It's about the boundary. The boundary is what determines whether you'll need to or not. Okay, so when y goes from 0, so that's the outside, right? When y goes from 0 to 3, what is the left and what is the right? The left is? So now I'm in 2 to whatever this is as an x value. So when we're between y equals 0 and 3, the left side is x equals 2. And then when we're between 3 and 5, the left side is what? So when y is between 3 and 5, the left side of this region is y minus 1. And the right side is still the same red line there. Does it make sense? Ask me if I lost you. So this is dx dy now. Ask me. If I lost you on number 3, ask. Lily, is it better? What's that? You don't know if it's better?
Oh, yeah.
So this is our left to right, bottom to top, right? dx dy, left to right, bottom to top. So we're looking at left first. This, what I've shaded dark blue here, that's the left side of this region.
You're gonna be on the outside of that circle.
And then the red is the right, so this is left. Left,
Oh, okay, I see what you're saying.
right.
Oh, and they get split up at the top where that blue thing has a corner.
We're doing tonight's homework. Finally. We did the one that was due today this morning. Thank God.
Any more questions about number 3?
So I think,
Any more questions about number 3?
We did a lot of
Daniel, are you good on number 3? Does that make sense? You guys in back, number 3, following it? Can I erase what I wrote on the screen? Okay, finally, I gotta go fast here. What's that? I said I gotta go fast. You wanna go faster than fast? So is this type 2 or type 1? The cheer is left to right, bottom to top. So the left side is x equals 1 half y. What is that? Like this? That's x equals 1 half y. Or y equals 2x. And then the right side is this. X equals, do you recognize what that is? Circle, radius 5, center at the origin, right? So it'd be x squared plus y squared equals 25. So this is 5 here. Okay, and so if we go from, this is left to right, are we in Exhibit A or Exhibit B? B, because this is the left side, right? This is left, and this is the right side. Okay, then from bottom to top, 0, down here, to 2 square root of 5. So 2 square root of 5 could be anywhere here, right? It could be anywhere, but it does turn out to be this intersection. So this is root 5 and 2 root 5. Gotta use the colors. Okay, and now we're going to rewrite this as what? Type 1. Type 1, first we look at bottom to top. Where's the bottom?
Y equals 0.
Is it split up or is it just one thing? Just one thing, right? Bottom. Bottom is just one thing, right? Top. What should we do? Quick, quick. Light brown? Not light enough.
Orange.
Where's the top of this thing? The intersection is not the top. In terms of, if we're doing bottom to top first, this whole thing is the top.
Okay.
This whole thing is the top. The top is the light blue. So, 1 or 2 double integrals? 2. So when, top left to right. So when we go from 0 to radical 5, what's our bottom and what's our top? So in this first, from 0 to radical 5, the bottom is 0. The top is 2x. That's this part over here. Then when we go from radical 5 to 5 in x, the bottom is 0 and the top is this thing, y expressed as in terms of x. So radical 25 minus x squared. Okay, I'll leave it up if you want to ask me on your way out.